So thank you for the introduction, Mr. Chairman. So as mentioned, my presentation is about Micro-Fluxgate. So Fluxgate is a magnetic field sensor, which is used for measuring DC magnetic field. So a typical application would be, for example, like electronic compass for navigation or contactless current measurement. Flux gates are typically large in size, like a few centimeters, maybe 10 centimeters. But today we will be talking about miniaturized flux gate. So I'll briefly start with some brief introduction of how flux gate works. So it uses nonlinear properties of ferromagnetic material. So we have a core made of ferromagnetic material, and we have an excitation coils that create magnetic field in the core. This field is alternating, but always the two parts of the core have the excitation field in opposite directions. And we have a sensing coil, and the flux goes through the sensing coil in one direction and in opposite direction. So in normal conditions, with no external field present, those two fluxes are equal and opposite, they cancel each other. Therefore, we have zero total flux in the sensing coil, we don't get any induced voltage. But if there is some external field, which is the field that we are measuring, if there is this external field, then one side of the core, it has the external field and excitation field in the same direction. The other side have them in opposing direction. So in one part it adds up, in the other part it subtracts. So this creates some asymmetry. And because the core is behaving non-linearly, because we drive it into saturation, then in this case, we get some non-zero total flux in the sensing coil that we measure as the induced voltage, and this voltage is proportional to the magnetic field. And the most important thing to take from this is that in order for the flux gate to operate, the excitation field, and therefore the excitation current, must be high enough to saturate the core. So when we are talking about microfluxgate, as I mentioned, we mean a flux gate fabricated by a means of micro fabrication. So the sensor that we designed and fabricated is based on a CMOS chip. It's only 8 millimeters long. As you can see, the coils are actually made using bonding wires. And the most important part of the sensor, which is the ferromagnetic core, it's made from 25 micrometer thick ribbon of amorphous metal. And this is important that we use 25 micrometer thickness of the material because that is the thickness that we can commercially purchase. And we evaluated the performance of the sensor. Here in this graph, we have like the dependence between sensitivity and the excitation current. You can see that when the excitation current is too low, we don't get any sensitivity at all. That's because we don't reach the saturation. Then as we increase the current, the sensitivity goes up. So this is the point where the core is getting saturated. And the region where we want to operate the sensor is somewhere slightly behind this maximum, where the sensitivity is stable. And as we can see in this picture, like this is at 100 kilohertz, is the bottom of this graph. And we can see that as we increase the excitation frequency, the sensitivity goes up, which is important because with the miniaturized flux gate, we have a limited number of turns of those coils for the reasons of fabrication constraints. So we need this high frequency to reach high sensitivity. But we can see that as we increase the frequency, then the current required for reaching the maximum sensitivity is also increasing. So while at the 100 kilohertz, the maximum is around 50 milliamps. When we get to this maximum, we need almost 120 milliamps to reach the maximum sensitivity, which means that we have around 500 milliwatts of power dissipation. These are results for the noise. So we achieved noise in order of nanoteslas per square hertz. So it's mostly below 10 nanotesla per square hertz. The minimum that we measured was 2 nanotesla per square hertz. However, that occurred at very low frequency where the sensitivity is also very low, so that's not much usable. And some optimum that we found is somewhere here at 3 nanotesla per square hertz. And in order to decrease the noise further, we would need to reach deeper saturation of the core, which would require higher excitation current. But if we increase the excitation current even more, that would like result in damaging the excitation coil by too much heat. So the typical approach to solving this is using pulse excitation. So the results I showed so far are with sine wave excitation. So the method of pulse excitation, the idea is that we use short pulses, which has enough amplitude to deeply saturate the core, but the duty cycle is low, which keeps the power consumption low. So we were expecting to reduce the power consumption significantly and to also improve the noise, but we didn't see such results. We were able to decrease the power consumption somewhat, but it came at the cost of also decreasing the sensitivity, and we didn't see any improvement in noise at all. And we think that the reason why the pulse excitation didn't perform as expected was because of the eddy currents in the core. Like the frequency of excitation that we use is already quite high, and if we use the short pulses, it has those higher harmonics, so the excitation signal is like multiple megahertz, and such frequencies can't penetrate into the core. We can see that even at 1 megahertz, we are unable to saturate the middle section of the core. We can see that the penetration depth is around 6 micrometers, while the thickness of the core is 25 micrometers. So from this, we can see that to improve the performance, we need to use thinner core. We need thickness maybe below twice the penetration depth, below 12 micrometers. And in cooperation with the manufacturer of the material, we obtained a thinned version of the material, which has thickness of 10 micrometer. The blue one is the original version, the 25 micrometer. After the thinning process, the coercivity increased significantly due to some stresses introduced by the brushing that was used to reduce the thickness. So we had to use annealing in order to restore the original properties. We can see that the pH curve of the thinned material is a little bit different than the original, which makes it a bit more difficult to compare the results, but we can get around that. So here are the simulation results. Here we have the blue one is the original, the orange one is the thinned version. So at 100 kilohertz, we can see that the sensitivity reduces a bit, and that's all. But what we care about more is the behavior at 1 megahertz at high frequency. Here we can see that the sensitivity is still lowered a bit, but the important thing is that with the thinner core, the maximum is now reached somewhere around 50 milliamps compared to like 100. So we have reduced the required excitation current in half. The yellow one, it corresponds to these slightly different properties. So we can see that thanks to the higher permeability of the actual pH curve, the sensitivity goes back up a bit. So these are the measurement results, and we can see that it matches the expectation from the simulation. So this is the original version, which reached the maximum at 1.6 megahertz and 120 milliamps. With the thinner version, we reached the maximum also at 1.6 megahertz, but with only about 60 milliamps. So we were able to reduce in half the required excitation current, therefore the power consumption is 4 times lower. We also see that the overall sensitivity increased, but this is likely more of a result of the slightly different properties of the material than direct consequence of the reduced thickness. And this is the noise. So in case of the thinned version, The noise is below 2 nanotesla for most of the regions, except those where the excitation current is obviously too low. So this is great reduction in the noise. And also, while in the original version, the low noise is mainly achieved like at the low frequencies. Here we have low noise almost everywhere, and the minimum that we achieved, which is 500 picotesla per square hertz, it's actually achieved somewhere here at the high frequencies, where the sensitivity is also high. So in conclusion, thanks to the reduced thickness of the core, we were able to substantially decrease the power consumption, and the optimal noise is achieved at the same excitation conditions as the optimal sensitivity. As for the further research, we need to research more into the thinning process and the annealing of the thinned material to improve the properties of the material, because as I said, the properties of the material degraded a bit after the brushing process. So as I mentioned, I am from Czech Technical University in Prague, and this research is done in cooperation with our colleagues from National Taiwan University of Science and Technology. And we would like to thank Taiwan Semiconductor Research Institute, because thanks to them, we have access to the chip fabrication technologies. And we also thank the Vacuum Schmelze company from Germany, who is the manufacturer of the material and helped us with the thinning process and provided the samples of the material. So this concludes my presentation. Thank you for your attention.